Welcome back, and in this video we want to take a look at the gradient descent method. This is a general concept that is very popular and very often used to numerically optimize the minimization problem when estimating models. So in this video we just want to take a look at it from a very general perspective, and again with a synthetic example which really is not really close to what we will experience when we work with real data, but I hope it serves to provide you a good intuition. And also I want to say this up front, even if you do not understand this concept right now, it's not a big deal, because you will not have to do this manually when you work with data, because there are pre-written libraries which already provide functions that internally use this method. But I think it is very important for you at some point in time to at least understand it a little bit, and the aim should always be that you could do it by yourself, even if you do not have to do it by yourself later when you work with real data. You should be able to do it by yourself, because if you do, then this means you really understand what you're doing here. And nowadays there are so many libraries available which enable users to use sophisticated advanced models without really knowing what they're doing there. And I think from a professional perspective, this is really not good, because at some point you will reach a situation where it will not work and the output will not make any sense to you, because you don't have any idea what you're doing here. So it's always important also to know the methods by yourself, even though you will not have to do this by yourself, or program it completely by yourself. Okay, so saying this up front, we will now go into the example of the gradient descent method. Okay, so what is the gradient? Why is it called gradient descent? We are always now in the situation that no matter which task we're given, no matter if it's a regression problem or a classification problem, we will have set up a model that we will describe by function f here, and the model will depend on parameters that we subsume by theta here. And usually we have an input which is given by a vector x. Okay, and this is what will generate our prediction, which we typically describe as y hat. And then we will have a loss function which compares the actual realization of the target variable y and its prediction. And the loss function is a feedback, so the better the estimate for y hat, so usually the closer it is to its target realization, the lower the value. And what gradient descent now looks like, or at what's important for gradient descent, as the name suggests, it works with the gradient of the loss function here. And so typically y hat, as you can see here, it depends on parameters. So let's make this clear by writing theta here in the subscript. And if we have, for instance, a model with one parameter, this is a model that we will take a look now, and if we have a regression problem, then for instance we have a very easy model with one feature variable that depends on one parameter, let's call it b, and times x, right? And the x is a given value, and b is something that is initialized by us typically randomly. So we could set any value for it, 1, 2, whatever, -3. And x is something which would be given, could be 20, for instance, at this moment, or in our example, it will be a value of 2. And now depending on which value we are, so let's make this more specific. Let's say we have one value of x, which is 2. And this is how our model looks like. So we can impact, or we can influence the prediction for y hat by setting the value of the parameter b. And now in the example, our true value will be 3. And if we use the loss function, which is the squared deviation here in this example, then we have y minus y hat. So with this, only with the single observation here, we have 3 minus b times 2. And we take a look at the squared deviation. And now the gradient here, it's actually only the partial derivative with respect to the parameters in the model. And here we have only one parameter, so it is just the partial derivative of the loss function with respect to the parameter. And yeah, by doing like basic calculus, mathematical calculus, we will find out that this is 3 minus b times 2, and now we have to use the chain rule, and this is how we end up with this partial derivative. And now what's important for you to understand is what's behind, or what does it mean, because depending on the value b that we will enter here, it will generate either a positive or a negative number. And we will see this in a moment, but I'm quite sure that you remember from school or from your initial math course that the derivative is something which tells you, is like analyzing the sensitivity of the function value with respect to a change in the input value on a marginal level. So like I try to make this easy. You can imagine how much does the function value change if we change the input value, which is b here, by a very small number. So we increase it by a very small number. So the gradient here tells us if this is a positive value, that means that increasing the value of b marginally will increase the loss value, so the value of the loss function. So if this will be the case, then this means increasing b in our case here, or in our situation, is not a good idea, because we want to decrease the loss value. So if the derivative, as it can be seen here, is negative, then this is good, because this means increasing b will decrease the loss value. Okay, and so we have probably like one of these situations. So either the partial derivative here is positive. If it's positive, it means we should decrease the value of b, right? Because if it's positive and we increase the value of b, it increases the loss. But as we want the loss to decrease, then we should decrease the value of b. And if the partial derivative here is negative, that means we should increase the value of b if we want to decrease the loss value function. Okay, so basically the gradient is just an information to us what to do, in which direction we need to alter the value of the parameter in order to reduce the loss function. And I think this is quite important to understand the meaning here, and not what's less important, to be honest, is for you to understand how you are actually determining the derivative for a concrete function, because this is something which will be handled by the computer for you. But I think for your understanding, it is really important to make sure that you understand what the gradient means. So in the most easiest form, let's just for 1 second go away from this example, and we will come back to it in a minute when we take a look at the collaboratory file. But assume we have some value of y that we do not know at the moment, and assume someone asks us to just guess a value for it, and we will do this by y hat. Now, if so, it doesn't depend really on the parameter, it just depends on our guess, right? And now if we take a look at the loss function, again, this is here, and let's just generate the derivative of the loss function with respect to our guess here. Then we have minus 2 times 1 minus our guess. Okay, and now we can have two situations. Assume now the true value of y is known. Now it's identified. Okay, so assume our initial guess was too small, right? So then the true observation here would be bigger than our initial guess. Then this leads to that we have here a positive number, and overall this means that we will have here a negative number, okay? And the negative number with respect to the content that we have here means that we should further increase our initial guess, okay? Right? And that makes typically sense, because if our initial guess is too low, and now we get the true value of y, then the gradient just tells us, okay, your initial guess was too low, you better increase it for the next time. And the same holds true if we would find the other situation. So that means if our initial guess is too big, then we have this here, then this here is a negative number, and overall this gets positive, and this means that the loss function would further increase if we would further increase our guess, so we should decrease it. So it just tells us your initial guess is already too high. If you further would increase it, it would be even way too high. So of course, if we're reasonable persons, then we obviously want to decrease our initial guess. Okay, so it's really important, I think, for your general understanding that you take that you understand the concept of the information which is provided by the gradient. Okay, and now last but not least, because I'm always talking of gradients, typically we will have the situation where our y hat depends on many parameters, and so let's say here theta is really a vector which has, I don't know, theta 1 until whatever. So let's say we have big T parameters. Doesn't really need to make sense right now, just we have many parameters, and so the gradient, which is typically written something like this, is, but we will see this really formally in the slides and anything, is just the vector with all the partial derivatives of the loss function. So that means in the first place we will have the information in which direction we need to alter the parameter, the first parameter, in order to further decrease the value of the loss function. And in the last entry, we will get the information in which direction we need to alter the last parameter in order to further reduce the loss function. And reducing the loss function is what we actually want to do, because this means calibrating the parameters of the model to the data that we observe. So we alter the parameters in a way that overall for the data sample we are observing, the loss function is the lowest, and this means the feedback that is provided is that our estimates are as good as they can be for the training data. Okay, and so now in the next step we want to take a look at this example, and not handwritten by me, but I prepared something here, and I hope this will make it easy for you to grasp the general principle, not just what the gradient is, but also how to use it in order to start with a random guess for a parameter and end up with a sophisticated guess of the parameter that best fits the data to, or that best fits the model to the data that we observe. And here we are in the Google Colaboratory file, okay? We go back to the situation where we have a very simple regression type problem. We have a data set that really consists only out of one observation with one true realization of the target variable and one corresponding value of the feature variable. So we have a single feature variable here. And the model is just simply one parameter b times the feature variable. And obviously we are looking for b such that our estimate, our target estimate, our prediction is equal to the true observation of the target variable. So as you can see here graphically, this just means we have a linear function or a linear slope, a linear function which goes through the initial point here and through the origin, and then we have here the true realization, and we're looking for the slope of this curve here such that it goes through this point. So this is what's behind this problem. Okay, so not a really sophisticated problem, but I think it serves to show you the basic principle of the gradient descent method. Okay, so the loss function is, if we set a value of b, then we can calculate the value here. Okay, so if we set the value of b to 1, then our prediction is 1 times 2, so it is 2, and we have 3 minus 2, and it's 1, and even stays 1 even if we square its value. And we can do this, like in theory, with every guess that we would have for b. We can do this for 2, for 2.5, and for 3, and so on and so on. And I mean, you can obviously see, and you wouldn't need any numerical technique here in order to find out the best value for b, which is 1.5, but you can see, depending on the value of b we are using, the value of the loss function gets bigger the more it deviates from the value of 1.5. And if we calculate the gradient at a certain point, so the gradient with respect to b is given here. We can relatively easy calculate this, I would say. And you know, it's like the tangency that you have here. So if we are at a value of 2, then it just gives you the slope if we would match here a tangent curve at this point at the function. And so if it's a positive value, that means we have an upwards linear curve here, and if it's negative, then it means it's facing downwards. And as I explained a few minutes ago, so if it's a positive value, that means, so for instance, if we are at the value of 2, then the value of the gradient is minus 2 times 1 times 2, so should be minus 4, should be plus 4. And then plus 4 tells us, so if you further, just the 4 is just not so important. Important part here is it's plus. So that means if you would further increase our value of 2, that brings us far away, or that increases the loss function, which is true, as you can see here. So if we are at the value of 2, then the gradient is plus 4. So we know that if we now increase it by a marginal amount, we will definitely increase the value of the loss value. So that means if we are here at this point and the gradient is positive, we should at least go into this direction. So we start searching for a better value of b than 2, but go into the to the left here, so go to smaller values. In comparison, if we are here on the other side, if we are at the value of 1, then we would get minus 4, and minus 4 tells us, okay, the loss value would further decrease if you increase the value here, so you should go to the right. Okay, so the gradient, the sign of the gradient, tells us in which direction we should alter our current parameter estimate in order to further reduce the loss function value. But now the next important question is, by how much should we change our current guess of the parameter estimate? And this is driven by the value of the gradient. So if it's 4 or 10, then it gives us the idea how steep it is at this point. And the more steep it is, the more we can reduce the loss value if we follow the correct direction. But we also need to take care of not to overshoot. So if we are, for instance, here at the point of 2, then with the knowledge that the gradient is positive, we know we need to further reduce our value. But if we reduce it too much, for instance, if we go to 1, then we overshoot it, and then we are in a different situation. So now the parameter estimate is not too big, it's too low. So it's best to use smaller steps, and smaller steps then, for instance, are suggested by the actual value of the gradient. So that is why we will have an update rule. And the rule is, if the value is positive, then we decrease our parameter estimate. If the value is negative, then we increase our parameter estimate. This update rule is given here. So we take the original value minus the gradient. For the moment, ignore please this eta here. And you now can think of, so minus, if we have a negative gradient value, minus something is plus, so we increase b by, so the new value of b will be bigger than the original value. And if the gradient is positive, then we have minus something positive, so we reduce the original value of b. This is exactly what we want to do if you compare it to the situation here. And now, in order to make sure not to overshoot, so not to correct the original value by too much, by too far, that we go too far, we will also use eta, which is just a constant numerical value set by us as the user, in order to make sure that we are really doing like smaller steps here. So eta is something that needs to be set by us, and we should try different values. It shouldn't be too big, because if it's too big, then we have the problem, or the probability for overshooting here is quite big, and that we end up with a parameter estimate that now goes completely into the other direction and is not too big but too high, for instance, or it's not not too big, it's too low, or it was originally too low, then it's not too big. But if we set eta too small here, then the original value really changes by only to a very minor extent. And of course, we will not do this only once, we will do this many times. So like we will talk of an iteration here, or an iteration step. So doing this once is one iteration step, but take a look here. For instance, if we start at 2, and now after one correction we end up with a value of 1.8, then of course we at the value of 1.8 we again should check the gradient, and so on, because what we're trying to find is approximately the point where the value of the gradient is 0, because if we are at the situation where the value of the gradient is 0, that means we are either at a minimum or a maximum, or at a change point from the function. And from a technical perspective, just to mention this in this situation, the loss functions we are usually using here are convex functions, and this means that if we really find the place where the gradient is equal to 0, then it is definitely a minimum, and we want to find the minimum of the loss function. Okay, but let's recapitulate here. So we have the idea of having a loss function. We have the idea of a loss function which depends on an estimate, and the estimate itself depends on parameters. So one could say the loss function depends on how we set the parameter value. This is what you can find here. And now we have the gradient of the loss function with respect to the parameter. And the gradient tells us, the sign of the gradient tells us in which direction we need to change our current guess what is the best parameter estimate. And now, if we have the information of the gradient, of course we want to change the parameter estimate accordingly. And we do this by this rule here. And of course we will not do this only once, we will do this many times, until, like, the goal would be that we reach a value of the gradient which is approximately equal to 0. That's like in the best case. Usually we will take a look at the loss function values, and we will stop at some point when we identify that the loss function value doesn't really change anymore. Okay, and so how does this in practice look like? We would start with a initial guess for the parameter estimate. We would set a learning rate, and then we would just do this here. So we use the gradient of this the current situation, so the gradient value, and then we will just calculate our new guess for the parameter estimate, which is the original one minus the current one, which is the original one minus eta times the value of the gradient at the moment. Do not get confused by how I write this down here. It maybe doesn't make that much sense if you are new to Python, but it will make sense to you once you are more familiar with Python. Okay, but it's more important for me is that you see here the basic principle, that you understand the basic principle, and yeah, I think we talked enough actually to at least get an idea about the basic principle, because for now you should ask yourself if your mathematical understanding is enough in order to understand what it means that we have a loss function and how the loss function is related to our model predictions. And then you should be able to create the link that the model predictions again depend on parameter estimates. So actually the loss function can be manipulated by choosing certain parameter estimates. Okay, this is like what you should understand in the first place. And in the second place, what you really need to make sure that you understand is the idea of using the gradient of the loss function as a source of information, how to change a parameter estimate. And once you combine this, then we end up with this iterative procedure, how to again and again and again adjust our current parameter estimates with respect to the information of the gradient of the loss function. Okay, and if you understand this, that's it. No more like this. This is the basic principle that is used here for like the most easiest model. But the good news here is that it stays exactly the same even for very sophisticated and advanced models. Of course, there are further small details that are actually not that small, but there are, like in a broader perspective, there are some small details how we can improve the process here. But I would not like to discuss this at the moment in order not to confuse you, because I think for the moment, if you understand this, what I said right now, it really makes absolutely sense, and it's perfect. And this is like the most basic and most important part in understanding what is meant by numerically finding an optimum, so the minimum of the loss value here with respect to the parameter value, by using an iterative method that depends on the gradient information, so the gradient descent method. Okay, and yeah, if we do this, for instance, here in our case for 10 times, you can see in the beginning we are we're starting with a parameter estimate that is too low. And this is information is given by the gradient is negative, so the gradient tells us, hey, increase your parameter estimate. And then we do this from 1 to 1.4. Again, in the next step, the gradient tells us, okay, better, but still too low, and so on and so on. And here, after the third step, at least with using 2 digits here, we already at the correct value, but you can see here the gradient information still is not equal to 0. But then after here, in this case, after certain steps, we really reach the true minimum here where the gradient is equal to 0. And yeah, you just cannot see this here because we're only using like 2 numbers here after the dot and not more. Okay, here's just another example, and still a very easy one, but a more realistic. So we would have multiple data points, 200 here, and we have like a linear regression model with a constant and a slope parameter. And I just want to show you, you really need to become familiar with this by yourself. But what I told you earlier is you do not need to know or you do not need to worry about how to actually calculate the partial derivatives, because this is done by, there are different libraries of Python that do it automatically for you. So I just implemented this here in order to show you how it works. So in Python, you would define a prediction function. So with 2 parameters here, which I call theta, you will generate predictions. Then we need a loss function, that depends on the actual target realizations, on the feature variables, and on the parameters, and inside it works with the prediction function. And now with this package here, with this function it automatically calculates the gradient of the loss function with respect to the second argument here, so which is the parameter estimates the current one. So just it really is complex if you just started with Python, and it's also complex if you never heard about it or seen it before. So please do not get confused by this or feel overwhelmed. This chat, the only signal I want to send here is that calculating the gradient is quite easy, because it can be done automatically by great libraries which are available in Python for free. And as you can see here, again, if we do the principle again, so that means we start with some values. So the true values here are -1 for the intercept and plus 1.5 for the slope. And here we start with 1 and 1. And we set again the learning rate to 0.1. And the principle stays the same. In the first step, we calculate the gradient. So this here is really the partial derivatives. So the first one is the partial derivative of the loss function with respect to a change of the intercept parameter. The second value in here is then the partial derivative of the loss function with respect to a change in the slope parameter. And then we use this information, so the gradient, and conducting here the update of the parameter estimates according to the gradient descent rule. And if we do this multiple times, then we can see here gradient values, they signal as we are used to. So this value is too big, this value is too low. That is why here the gradient value is positive and here is negative. And accordingly, we update the parameter estimates, as you can see here. So here you can see the journey of the parameter estimates, and you can see they end up, more or less like to the true parameter estimates. The fact that they are still deviating here from the true ones doesn't depend or is not because of the procedure here is not able to detect the true parameters. This is just because we randomly sampled data here. And with random samples, you will never get the exact same values. You will get small deviations because of the randomness in the data that is brought into the model here. Okay, but here you can see again that the basic principle is really exactly the same, even though we have a slightly more complex model than we have in this example above here. And the good thing is this also works if we have, for instance, like more advanced models. Okay, that's enough for the moment. Okay, I really hope that this will, further help you to at least get some intuition what is behind gradient descent and how you can imagine how the models are estimated or are calibrated numerically. If this is not the case, then maybe for the moment just ignore this video and maybe come back later once you're more familiar with the different methods. But as I said in the beginning of this video, I really think it is important to at least have a good intuition for these kind of procedures here, even though if they are done by the packages or by the computer for at a later stage when we are really using the methods with real data. Okay, so take care and then see you in the next video. Bye bye.